in this problem, we're looking at a sequence of n independent events. So we have n independent events, and each event ends in either success or failure. So it has two options, and we're going to let p sub I be the probability that ith event is successful. So we are also given that we're going to denote q sub I to be 1 minus p sub I, so the probability that the ith event ends in failure. And we're also given these b sub i's, which are defined as q sub I minus 1/2. And we're also going to look at the event capital A sub n, and this event is the event that the number of successful trials out of n is even. So in part A of the problem, we're asked to show that for n equals 2, probability of A sub 2, in other words, the probability that out of two trials the number of successes is even, is equal to 1/2 plus 2 times b1 times b2, where b1 and b2 are defined as such. So q sub 1 minus 2 minus half and q sub 2 minus half. So to prove this, we're going to first notice that, so the probability that out of two trials we have an even number of successes, so that can happen in two ways. That can happen either if both trials are successful or if none of the trials is successful. Because if only one trial is successful, we're going to have odd number of successes. So, and the probability that both trials are successful is p1 times p2, and the probability that both trials end in failure is q1 times q2. And now we're going to rewrite p1 and p2 as 1 minus q1 and 1 minus q2. And q1 and q2 we're going to rewrite as b1 plus 1/2 and b2 plus 1/2. We can see from this very definition of bi that if we move the 1/2 to the left, we're left with qi on the right side. So we can replace the q1 with b1 plus 1/2 and q2 with b2 plus 1/2. And now 1 minus q1 we can replace with b1 minus 1/2, and 1 minus q2 is b2 minus 1/2 plus b1 plus 1/2 times b2 plus 1/2. So applying the distributive property, distributing out both sets of multiplications and simplifying, we get the desired result. So 1/2 plus 2 times b1 times b2. Now in part B, we're asked to show by induction the general version of part A, whereby the probability of A sub n equals 1/2 plus 2 to the power n minus 1 times b1 times b2 times ... b sub n. Okay, so in part A we already proved the case for A sub 2. Now we need to prove this. So now by induction we can suppose, true for n minus 1. So we're going to suppose the statement is true for n minus 1, and we need to prove that the statement is true for n. Now, probability of an equals, and again, just as in part A, we're going to reason in the following way. So if we're doing n trials, the probability that there are even number of successes can be broken down into two scenarios. Either the last trial, the nth trial, was a success. So the nth trial was a success, and then and then out of the n-1 trials we had odd number of successes. So the probability that out of the first n-1 trials we had an odd number of successes, given that the nth trial was a success, or the nth trial was a failure. So this will be q sub n times the probability that out of the first n-1 trials we had even number of successes, given that the nth trial was a failure. So S sub n complement. And by this notation S sub n, this will be the event that nth trial is a success. Okay, so what do we have here? We have P sub n times. So notice that by the inductive hypothesis, we know what P of A sub n minus 1 is, and P of A sub n minus 1 is independent of the nth trial. So this just becomes 1 minus probability of A sub n minus 1 plus Q sub n times the probability of A sub n minus 1. So we get P sub n times 1 minus 2 to the k minus second power, or excuse me, 1 minus 1/2 plus 2 to the n minus second power, b1, b2, dot, all the way to bn minus 1 plus q sub n times the probability that out of the first n minus 1 trials we had even number of successes, and we know what that is. So by, again, using the inductive hypothesis, this is 1 over 2 plus 2 to the n minus 2, b1, b2, dot, b sub n minus 1. Now simplifying the expressions, we get P sub n times 1/2 minus 2 to the n minus second power, b sub 1, b sub 2, dot, b sub n, plus q to the n, 1/2 plus 2 to the n minus second power, b sub 1, b sub 2, dot, b sub n minus 1. So this is minus 1 here, and here we have minus 1. And now what is this equal to? Well, distributing out remember that Pn plus Qn is equal to 1. So what we get here is if we distribute the Pn and distribute the Qn, the Pn times 1/2 plus Qn times 1/2, that's just 1/2. And then we have Qn times this expression here minus Pn times this expression here. So we have Qn minus Pn in parentheses times 2 to the n minus second power, b1, b2, dot, bn minus 1. And now we can write the Qn minus Pn. So this Qn minus Pn becomes 2b sub n. So we have 1/2 plus 2b sub n of this expression here, b1, b2, dot, 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 p n minus 1. And multiplying the 2 by the 2 to the n minus second power, we get 1/2 plus 2 to the n minus first power. And then moving the b sub n all the way to the end, we get b1, b2, dot, 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 b sub n minus 1, pn. So we've proven the desired result. Now, moving to part C asks us to look at some specific cases, some sort of extreme cases of values of p, and seeing how this answer that we just got, this answer here, whether it makes sense or not. So, the first case is that p sub I equals 1/2 for some I. So for some trial I, the probability that the trial is successful is 1/2. So one thing here to note is that if the probability of success is 1/2, then the probability of failure is 1/2 as well. And if we look at the definition of b sub I is qi minus 1/2. And so bi then becomes 0. And if one of the bi's is 0, then the whole expression 2n minus 1 b1 b2 dot 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 bn minus 1 bn, this whole expression becomes 0. And so the answer, the probability that out of n trials we have even successes, becomes 1/2. So if at least one, if even one of these n trials has a probability of success being 1/2, then out of the total n trials, the probability that there are even number of successes is 1/2. So another scenario we want to look at is that pi is 0 for all I. So what does this say? This says that all of our trials are going to fail. So if all the trials are failing, then we have, what do we expect to get? If all the trials fail, we expect the probability of even number of successes to be equal to 1, because the number of successes will be 0. All the trials will fail. The number of successes will be 0, so the probability of even number of successes is 1. So let's show that. So if pi is 0, then qi is 1 for all I, which implies that bi is 1/2 for all I. And so if bi is 1/2, this expression here, 2n minus 1, b1, b2, dot, 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 bn minus 1, bn, this expression becomes 2 to the power n minus 1 times 1/2 to the power n. And this is 1/2. And now remember that probability of a sub n is 1/2 plus this whole expression, b sub n minus 1 bn. So this becomes 1/2 plus 1/2 equals 1 as expected. And then the third scenario we want to look at is the scenario where p sub I is 1 for all I. So p sub I is 1 for all I. So this says that all of the trials are successes. So if every trial is a success, what is the probability that there are even number of successes? Well, it depends, right? It should depend on how many trials we perform. If we perform an even number of trials and all of them succeed, then we'll have even number of successes. But if we perform an odd number of trials and all of them succeed, then we definitely will not have an even number of successes. So let's see if that's reflected in the answer. So if pi is 1 for all I, then q sub I is 0 for all I, which implies that b sub I is negative 1/2 for all I. And so, again, the expression 2 to the power n minus 1, b1, b2, dot, 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 bn, n minus 1, bn, this becomes 2 to the power n minus 1 times negative 1 over 2 to the power n. So if we factor out the negative 1 to the nth power, we get negative 1 to the nth power times 1 over 2. And so again, we remember that the probability of even number of successes is 1 over 2 plus this expression that we just found, so negative 1 to the n times a half. And what does this say? This says that if n is even, then probability of a sub n is 1. So if we perform even number of trials, we definitely have even number of successes. If n is odd, then what do we have? We have p of a sub n equals 0. So if we perform an odd number of trials, then we cannot have even number of successes. Since every trial counts as a success, if we have odd number of them, we have odd number of successes. And so this expression reflects that idea that the number of successes will be the number of trials we perform. So to have even number of successes, we want to perform even number of trials.